the recording. Okay, so welcome to Madara Community Call number 8. Let's go through the agenda. I think today will be pretty short, especially because Matthias is sick and will likely don't join. So that means that we will do a brief project backlog review. Then we'll have Tariq presenting Moro, which is a project they built during the Pragma hackathon. And then we will we'll talk a lot about the proving and net availability, specifically about the work that Ben initiated and how it can enable other people to start working on adding other data availability solutions like Avail or Celestia or EigenLayer. And as shared in the group, we now have the telemetry set up for the Sharingan testnet. So you can just add a parameter to your node command, and you will be referenced in this UI. So that's pretty cool. And we'll set up a proper subdomain name to point to the service. It will be easier. Yes. Okay. So let's start with the first item. Quick project backlog review. So if we go through the latest pull request, so we have Lana. She's not there. Okay. We have few improvements like the protocol version that is now U8 and not a string anymore. We have more tests in the block proposer logic. And that's good because this one we copied it from Substrate clients. And we need to also to add more tests specific to our custom logic. So for the moment, we have changed only a few parameters like the time left for finalization, stuff like that. We have changed a bit the parameters, but nothing more. This one fixed remove wrappers was a pretty big one. It had a very big impact in terms of performance. Let's see the graph. So this one, basically this PR. The main difference is that now we are using the types directly from the blockifier. Maybe Lucas, you can explain what it does exactly and why we have such a significant gain.
Yes, so Substrate requires a specific trait because it has its own encoding thing. So we have to derive some traits from types, but the blockifier was underwater for 12. So we just created wrapper types with a Substrate native type. And converting from those types to the blockifier type was super expensive. So we lost a lot of performance there. And we implemented them in our port. So now we're back to better performances.
Nice. So we are around 115 TPS for AC20. And near 100 NFT means per second, which is great. And we are at more than 200 TPS on a MacBook M2. So that's pretty cool. Okay. Another big feature. Initially, we wanted to do a deep dive on this feature, but Matthias is not there, so we'll do it next week. But basically, now we have the global state root computation. And the cool thing is that it's one example of an optional feature that you can add or not in your app chain. Because it has a pretty significant performance overhead, we wanted to make it optional, basically. And to be explicit, for the benchmark, we are not using it. We wanted to make it configurable and optional. Because this is the whole idea of having a modular stack that enable to choose different behavior for different app chains. So this was one of such example. So that's pretty cool. And then we want to do some optimization in this area because for the moment, the global state root computation is computed on the runtime. And it's pretty slow, and we want in the future to compute it on the client side. and to in the block header of the block n, we will in the future include the state root of the block n-1 that will enable to do that computation asynchronously, basically. Okay, and this is very likely what will be done in the public staffnet in any case, because the overhead in terms of performance is pretty big. And then few improvements. Okay, so I will now let Tariq present the project hackathon that Carbonable built during the Pragma hackathon.
Yes, thank you. Let me just share my screen. Can you hear me?
Yeah. Yes, we can.
Okay, great. Okay, I'm screen sharing. I'm not sure. Just tell me if you can see my screen.
Yes.
Yeah, we can see it.
Okay, great. So, I'm Tariq. I'm working at Carbonable, and right now I'm going to present the hackathon project we submitted for the Pragma hackathon, which is called Moro. Which is
maybe you can give a quick overview of what Carbonable is, because it will help to understand the context of Moro.
Sure. Yeah. So Carbonable is a protocol that is built on Starknet, and the idea is to bring crowdfunding for decarbonation projects. So basically, we help project developers to crowdfund their forest or mangrove projects. We help them develop it and finance it, and when it's financed, then users that participated in the financing of the project have a NFT that represent their share in the project. And once they have this proof of participation, they are able to claim either some yield from the farming, because they can either choose to sell the carbon credits or they can choose to offset them. And we give them the possibility to do that through our contracts, so it's traceable. And also we have a front end to help consumers as well as businesses. So this is a quick overview of what Carbonable is doing. Also, we have a labs where we are trying to bring all ideas from blockchain, like decentralization and the core ideas into Carbonable. So we also work on dynamic NFTs and on-chain stuff, and soon probably some zero knowledge also directly integrated in our protocol. So yeah, so that's Carbonable. And so right now, in part of the Carbonable Labs, we decided to try to learn a bit about Madara, and the project that made sense was to, it's called Moro, and it's a way to add block decarbonation on top of any Madara-based app chain. So this is what Moro does. So quick presentation. So Moro, as I said, it operates on top of Madara, so directly at the sequencer level. And basically, it enables block producers to offset blocks. So it offsets the carbon emissions of every transaction computed with respect to the transaction execution resources. And it aims to do so automatically, probably, and traceably. How it works? So we enable block proposers to add a special transaction. And this special transaction will actually buy the carbon credits that will be needed to offset all of the block resources. And the idea is that the payment, the payment to buy this offset is directly deducted from the fees the sequencer will receive from each block. In more details, what happens in Madara is that we have a contract that is deployed at Genesis, which is a carbon credit pool. We also how to say, we need the carbon offsetting cost to be fetched from an API, because we need to be able to map execution resources to cost to actually compute the carbon emissions. And we also needed another thing that we added to the block header, which is the block total resources, which was not available right now. So we added it in the block header. And so once we have all that, we are ready to send a local transaction. So what happens is that during the block finalization, we have computed all of the resources. And so we are now able to compute an amount of carbon credits that needs to be bought to offset the current block. And of course, so this is just a general idea. We can probably choose to, let's say, offset every 100 blocks or so. This is a kind of modular. So this is the base idea. And yeah, I will probably first show what's going on with the code. So as I said, we need a way to buy credits. So the way it's done is we deploy an ERC20 contract at Genesis with a special with an extra method that will allow people to buy some offset. So all that this method does is just transfer some. So it's just a way to buy credits. So we just mint some carbon credits, provided that we have a payment from the payment token. Of course, the payment token here can be set to anything, but I think I set it to the fee token. Once we do that, so once we have this, so it's a Kiro 0 contract because I couldn't have a Kiro 1 contract, but it's basically the same idea. It will probably be a Kiro 1 contract in the future. And this contract is deployed at Genesis. So we add it to the runtime Genesis config directly. So it's here. And of course, we added some constructor thing here directly at Genesis. What we added also to the code base is what I said is the block resources. So right now the block resources is just the total amount of L1 gas, step, Pedersen built-in, and wrench check stuff. And this is added directly in the block header. So this is the header, and we added it at the end. So in order to compute that, we need that in the library. Each time there is a transaction, we update it actually. So the transaction is run. We have the resources of the transaction, and each time we added this piece of code so that the resources are up to date every time a transaction is made, which means that at the end of the block, we can call this extra palette function, which will actually send a local transaction. So how it works is that this palette function is called on the onFinalize hook. And it's basically just constructing transaction that will be added. So the transaction is a transaction that is made by the sequencer account. So we assume there is a sequencer account. And the sequencer account has probably some fees from every block he constructed. So he has some amount of money, let's say, and it will just make an email call to our carbon pool address, which is deployed at Genesis. So we construct this transaction. We compute the actual amount using the carbon offset cost we fetched, and we execute the transaction. And at the end, once the transaction, we get the if the transaction executed well, then it's added to the pending to the pending transaction. So it will get added to the StackNet block during the store block function. So that's basically the main idea. I think I'm open to any comments because so this is as far as we got. We have a lot of stuff to do also to continue. Most the most important one is, so yeah, here we need probably that this extra transaction to be added to the actual block. We probably need that it's an inherent transaction so that it gets shown to, it gets added to the block. And the end game also would also be to take this code and implement it as an extra palette so that it can be used by any substrate blockchain, I'd say. And yeah, and right now there's no front end to show what's going on, but the idea is that since once we get each sequencer to have some block decarbonated, then since the transaction should be shown in the block, then we can have some kind of leaderboard to show how much one specific sequencer has decarbonated. Yeah, and that's it.
Thank you very much. That's very cool. I think one thing in the future that could be great is to have the logic of computing the amount to offset through a Cairo program to make it provable instead of calling an external API, because I think the computation should be pretty simple. Maybe there are some discussion around the upgrade of the computation. I don't know if this is a formula that is changed frequently, or but yeah, I think in the future it could be very interesting to have a provable computation for the to avoid depending on an external service for the offsetting costs.
True. Yeah, because right now what we thought is that we will fetch data from an API to get the exact amount of costs. But it's not clear how this could be computed because it's not really. It might not be just constant. It might depend on the on the machine, right? So yeah, but yeah. It would be nice if this. Even this could be probable. Yeah, I completely agree.
Okay, very cool. Thank you very much. I think we can move to Ben, actually, talking about the proving.
That was a super cool presentation. I wonder if you could come up with like some base unit for a Cairo step and charge that. Like what's the average amount of resources on an average machine that a Cairo step would take? But you're going to be approximating, I guess, at that point.
Yeah, I agree. Yeah, and also there's the execution, but there's also the proving, right? And I think the main idea is to first probably find out which part is the bottleneck, actually.
Yeah, but you know what? Ultimately, we want the fee model to reflect exactly that, the amount of work done by the sequencer. This is already a difficulty we have for StarkNet. So I think in the future, we can rely on that because the work will be done to map the fees to the actual amount of work, etc. So I think it can be a useful metric in the future. Let's say once we have something like a multidimensional EIP 1559 fee market. Anyway, that's very interesting. Looking forward to. I think you should speak with the actual AppChain project that will want to use it. Actually.
Yeah.
Yep, super cool. Okay. Can you guys see my screen?
Yes.
Yes, we can.
Okay. So I'm just gonna go over why what was implemented. We went over this a little bit on the last community call, maybe 2 community calls ago, so I'll just highlight it. The steps that we need to do to make data available, both for proving and non-proving contexts are as follows. We need StarkNet and Madara to submit a position independent execution called Pi to the Sharp, the shared prover. That shared prover is sitting off chain. It handles the position independent executions of multiple platforms besides StarkNet. It handles StarkX computations as well. And it writes to a Stark verifier written in Solidity that's on L1. And then once we know that that proof is available on L1, the sequencer writes the update to the core contracts on L1. So there's two different ways to think about this. One is that this is the canonical sequencing of StarkNet. This is the way it works today. This is what I tried to emulate, but in a fractal model, this would just be one layer higher, right? So Ethereum L1 would essentially be StarkNet L2. These core contracts would be Madara core contracts written in Cairo. And then the Stark verifier would be written in Cairo as well. So you can take everything I'm talking about today up one layer higher. Because we do have core contracts written in Solidity, we'll look at those real quick. So this is the update state function written in Solidity that sit inside these core contracts. The interface here is, and this is step 4. So this is after we know we have a good proof available. We're going to get the program output from the run of the StarkNet OS. And that represents the state change of all of the storage changes that occurred during this block on StarkNet, or in this case on Madara on our app chain.
Maybe you can explain a bit what is the StarkNet OS, because I think this is a notion that is not well known, actually.
Yes, the StarkNet OS is a collection of syscalls written in Cairo that make all of the state change from, we have this storage, this Merkle Patricia trie that handles the contract storage for each contract on StarkNet. Now we take that as the initial state of our blockchain, and we run a program on that blockchain, which is the StarkNet OS. And that StarkNet OS affects the state of all of the contracts that are stored in that trie. And then we end up with a final state, an S1. So the StarkNet OS is the process by which we mutate our blockchain from S0 to S1. But it's written in Cairo, so it's all provable. Any questions on that? Okay. So the program output then is proof. It is proof that these state changes occurred at L2 and are available on L1. So if you do want to go through and read this entire code base, you'll see that this is all done by way of facts. We don't actually have to interface with the facts. The facts are computed inside this function. And then those facts are checked against the verifier. That's a little bit outside of the scope of what we're going to talk about today. But the verifier basically encodes these state transitions in facts that it is proving through its execution. So program data here is the really important thing. This program output is the program output from the StarkNet OS. These are from the docs, the StarkNet docs. They have a good example. This Zoom is screwing with me, one sec. Okay, so this is the program output as it's encoded pre v0.11. So, it's basically what I said, it's just the contracts that were deployed. If a contract is already deployed, it is the state, the storage difference that occurred for that contract. And then the nonces that have changed from the signatures. So these are the things we need to know about L2 to prove that the L2 state has transitioned from S0 to S1. Okay. And then there's a little example here of how that's encoded. So this is obviously a array of call data that's all UN 256. Okay, so we'll get into what's been done on Madara and what should be in this PR. Okay, so we have the sequencer, and we spin up a node. So the tasks that the node then needs to handle, and they are somewhat asynchronous because the prover sits outside of the context of Madara, is that we need to come up with a position and independent execution and encode the state diff. And then we need to send the position independent execution to the prover. And then we need to query when that position independent execution has been proved successfully to the verifier. Once the verifier has said, yes, this exists on L1 or L2, we can write the state. Okay. So here we have two different handles then. So we have two different spawns, one for proving and one for updating. So we can handle the asynchronous nature of this. DA worker prove and DA worker update. This is all in data availability lib. Okay, so what does the prove current block do then? So the prove current block sits on the store. This is all on the client side, by the way. So it sits on the client and it reads from the stream of storage change notification stream. So every block we get notified of what the storage change set was. Now this is all from the substrate MPT. So we have to index into it in places that we know that these things exist. So here on line 21 to 29 to 28, we have the storage prefixes for where these things are. So, and I don't know if Timothy is on the call, but there's probably a better way to do this than what I'm doing. But he can comment in the PR. So here is the storage prefixes. This is the in the palette nonce, in the palette starknet, in the starknet nonce, we know where in the MPT this exists and where the storage change as it comes through will sit in the MPT. And this way we can index into it on the client side instead of having to do all of this in the runtime. Okay, so we get all these storage event notifications for the block. I won't go into this too much, just know that this is encoding the change set into on the left. This is encoding the change set to what looks like it on the right. And this is what the Solidity contracts are expecting, is this format of UINT 256s. Cool. So then the next piece, on line 72 here, because we have this asynchronous nature, which is we don't know exactly when the sharp is going to write, we need to store this information on the client side for retrieval later. So we have a client side database in the key value store that's been added. It's called DADB. And let's look at some of the key values it stores. So it's going to store the state diff, and it's going to we're going to be able to get the state diff later. The sharp actually mints a unique identifier, a job ID, so that we can query it. So we store the job ID and we can fetch the job ID. And then just to make sure that we're operating on the same last prove block, the core contracts have this ABI that's exposed that is what is the last prove block. So we'll just make sure that we're operating on the last prove block. We're not sending an update state for a block that's not proven. So that's what's in the DADB. We'll go back to the business logic here. On 72, so we store that state diff because we don't want to write it now as the block isn't proved yet. And what we do is we submit the PI. We submit the position independent execution for the prover to run. So submit PI, there's some sharp utils here. This is just going to interact with the sharp. It exposes a couple different endpoints. One is the ability to add a job, and one is the ability to get the status of a job. So these are just kind of, stock REST calls for submit PI and get status. Okay, assuming that the PI submission went through, we will then update the Cairo job in the client side DB. And then the prover can then operate on the next block as it gets it. Update state then. Update state sits in the import notification. So it's going to get a block import notification. It's going to say, okay, we have a block. What is my task? Well, my task is to find the last proven block, make sure that I'm not sending an update for something that I don't need to. Get the status from the sharp of where that is in its proving context. If it is proved and on chain, if you are curious about what the values sent back from the sharp are, they're here. So unknown, not created, in progress, processed, on chain, invalid, and failed. So this process will then take its cue. Right now I just have on chain, but we'll obviously need to make this more robust. So if that job is on chain, we will fetch the state diff and we will write the state diff. So what we don't have right now, and I need to get by the time I submit this PR, is this little function block, which is going to publish the data. So we're going to publish the data and update the state. of the core contracts. That is pretty much it. Are there any questions?
Thank you, Ben. I think it will be a goldmine of information to understand how it works, because I think right now it's pretty opaque in the current architecture. So I think it will be very helpful for people. So once we have this initial PR, we need also to work on some documentation, some flows, some diagrams to show the exact flow. And as you can see it, we will need also some kind of abstraction layer. For example, on the published data, as Ben said, we want also to be able to use not only Ethereum, but also Starknet L2 as a data availability layer. So we need some kind of abstraction and configurations through the node to be able to choose between different data availability solutions.
Yep, 100%. Yeah, I want to either implement or open up issues to basically, make published data a trait that needs to be implemented, and then we can basically have that written anywhere you want and configurable by the node. But yeah, as far as documentation and everything, I work for Starkware, and it took me a long time to parse through all this information.
Yeah. Honestly, before your work on that, even for me, it was not clear at all. So thank you for this. It's very helpful. So I can't even imagine for people that don't work at Starkware. So yeah, this is very useful. Yeah. Hello? Okay.
I have a question.
Yes, please.
Yes, I'm just wondering. So, do I understand correctly that we get the state diff from Sharp?
No, the state diff is going to come from all of the change set that occurred during the block.
Okay, I see. Now, so my real question is it possible to access data from another chain, since Sharp is, as you said, doesn't know where the, let's say, the transaction come from? It could be StarkX, it could be another Madara app chain. And is it possible to have some kind of, let's say, inter-blockchain communication that way? Like accessing state diffs from other chains, like let's say accessing StarkX state from Madara. Is that possible?
You could, I mean, that you definitely could come up with something like that. That doesn't exist today, but I mean, you could have some type of aggregation layer where all of the state diffs from the different chains are posted. I don't see a reason why you couldn't do that. Yeah.
Okay, that's cool.
I have sorry.
Maybe Starknet itself just becomes that. Once the fractal scale, like let's say that all of these app chains do exist at L3, they're all going to have to post their state diffs to L2. So maybe Starknet itself just becomes that aggregation layer. I don't know. It's a good question.
Yeah. I guess we'll see some kind of a bit similar to shared sequencing, actually. Some specialization of entities that will provide this job. Then, of course, you need to think about an incentive model, etc. But yeah. And Pilo, you had the question?
Yeah, thanks. Yeah, I was wondering about like the publish data function. I know it's still work in progress, but could you maybe like just explain a bit like what would be the differences between having Ethereum as a data availability layer compared to Starknet? I mean, what would be like the difference inside this function? What would be, because I have a bit of trouble understanding how this part works. So maybe like how the difference between yeah, could you publish data to Starknet and versus Ethereum?
Yeah, so essentially, I'm probably gonna get this syntax wrong, but anyway, so yeah, the first thing that here is going to be the signer middleware, right? So the signer middleware is going to be an EOA that controls some amount of funds because it's going to need to pay for this transaction. So, but you know, all of that to say that's all Ethereum based context. So this published data is going to be very specific to Ethereum. The next published data for
any other EVM chain, by the way, not
or any other EVM chain, right?
Yeah.
This for Cairo then will be like, let's just say it's felt you know, whatever it's felt felt the signer here is going to be the signer of a not an EOA then, but a Starknet account. You know,
and just instead of using Ether's RS, you would use Starknet RS to submit the transaction, stuff like that, basically. Just small difference to have this, yeah.
Right. And then this contract address is not going to be a contract address on L1, but it's going to be a contract address on L2. It's so on and so forth.
Okay. Okay. So yeah, the like the core concept doesn't change. It's just adapted to what's live on Starknet, right?
Right. Right.
Okay. Okay. I see. Thanks.
Yeah. The good thing is that it's only data, so there is no core logic there. You need to take the data that are formatted before, and the formatting of the data can be the same. And then, yeah, it's just the transport layer and yeah, where you send the data. But yeah, there is no business logic in the published data.
Okay. 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 That's what I was wondering. Exactly. Thanks.
I think eventually, once we do want to start sending data blobs, I do think that there will be that type conversion in this function, you know,
yes.
Everything. Yeah. Okay.
Exactly. Yeah, for those who don't know, block transactions, this is the EIP 4844, also called proto-donk sharding. That is specifically implemented for layer 2 operators to submit data in a cheap manner. And also it has a separate fee market, different from the fee market for the gas. You know, because it's important to have this distinction, because for the moment, if there is a spike of usage on the L1, the price of the gas will increase, and then all layer 2 operators will suddenly pay much more to submit data, because we use cold data, and the unit for pricing for cold data is the gas, which is the same for computation. So with this separation of fee market for data, you don't have the same, it's better. So if there is a spike of usage on the L1, it won't affect the price to submit data for layer 2 operators, and vice versa. If there is a spike in usage of layer 2, it won't affect the cost of the gas on the layer 1. And this will introduce a new type of transactions, which is different from the type of transaction that users submit. And those are block transactions. And there is a small difference because those transactions are gossiped only on the consensus layer. You know, on Ethereum now, there is the execution layer and the consensus layer. And those block transactions will be gossiped only on the consensus layer. But there will be the possibility in DVM to check the commitment of those data. Yeah. Okay. Is there any question, comments? Okay. I guess we can probably stop there. Okay, then